This is a short video retouching on the idea of how we deal with mass-to-mass conversions in stoichiometry. This is also in the live session, but this is just more of a brief overview of it. So remember, whenever we do stoichiometry, we're always looking at the 5 steps. Balanced equation, convert known values into moles, determine your limiting reagent, determine your number of moles of unknown from your moles of known and the balanced equation ratio, and then convert your unknown value into whatever unit you want it to be in. So last time when we did mole to mole conversions, we kind of skipped over step 2 and step 5 because I gave you the value in moles and I wanted it in moles at the end, which is what you come out of step 4 with. So you didn't need to worry about step 2 or step 5. Now we're going to go back and look at step 2 and step 5. And the good news is you've already done the stuff that you need to do here. What we're doing in step 2 and step 5 in a mass-to-mass conversion is we're going to use molar mass, right? We're going to have a mass that we're given, and we're going to use molar mass to convert that into moles. And then we're going to use molar mass again at the end to convert the moles from step 4 into some mass for step 5. The reason we're doing this is, like I always said, I don't have a scale that tells me moles. I have a scale that tells me grams. So I have to deal with real world units, so I've got to account for the fact that the measurements I get and the measurements I have to give back have to be in real world units, which are going to be grams or some other measurable quantity, but not moles. So let's skip forward to an example. Now I'm going to go through these examples fairly quick. You are more than free to pause them, try to work them out yourself, because I'll be doing them stepwise. So if you think, hey, I want to try to do this step, stop it, try to do it, go through. So we're going to look at the equation we looked at last time, the acetylene combustion. So C2H2 is acetylene, reacts with oxygen to produce carbon dioxide and water. Now last time when we did this, I said, hey, you have this many moles of acetylene, how many moles of water do you produce? Or how many moles of carbon dioxide do you produce? Now I'm going to change it up a little bit. I'm going to say you have this many grams of acetylene. So how many grams of water vapor do you produce? Now again, I've said excess oxygen, so we know step 3's still not something we're dealing with. Limiting reagent, you only got one reagent, so by definition it's limiting. So our first step, balanced equation. I already gave that to you. All right, step 2, convert my known value into moles. So this is where you would take the 12.4 grams, use a molar mass conversion, and convert that into a number of moles. So like I said, you can pause it, take a minute, try to figure it out. Hopefully you come up with something that looks like this, right? 26.04 grams per mole for C2H2, so that means you'd get 0.476 moles of C2H2. Again, step 3 is irrelevant because we only have one unknown, or one known, so that's our limiting reagent. So step 4, convert my moles of known, which is what I've got here, into moles of unknown using a ratio from the balanced equation. Now remember, the ratio is always the coefficient of the unknown over the coefficient of the known. So again, pause it, take a second, try to figure it out. So hopefully you came up with a ratio of 2 to 2. Yes, you can reduce it to 1 to 1. I just tend to stick to the coefficients as they are in the equation. Makes it easier for students to see the connection between them. So I got a 2 to 2 ratio, so that means effectively 1 to 1. So I'm going to have the same number of moles of water, which I need to correct that. That should be water right there, and it's not, but I will change it later. So moles of water, 0.476 moles of water. Okay, step 5. Convert your moles of unknown, which is what I've got here, into desired units. Well, desired unit here is grams. So again, molar mass calculation. Take a second. Again, this is water, not acetylene. take a second, see if you can convert this into moles, grams of water. So pause it here, take a moment, try to figure it out. Now that you've unpaused, hopefully it looks something like this. Right? So you get 8.58 grams of water for 12.4 grams of acetylene. Right? Really, the only thing different from last time we did this is 2 molar mass calculations. That's it. That's the only difference between a mass-to-mass conversion and a mole-to-mole conversion. So let's look at another example. So this is production of lithium chloride from lithium and chlorine gas. As I said in the live session, I would bet money, if I was a betting man, that in any part B I would give for this unit, there's going to be some diatomics used, and I'm not going to give you the balanced equation that the diatomics are in, because it's a great way to test whether you know your diatomics, and it also will throw off your ratios if you don't. Because if you were to have to write this equation out just from what you read above, lithium with chlorine forms lithium chloride, and you didn't remember chlorine as a diatomic, that would give you a 1:1:1 ratio rather than a 2:1:2 ratio, and that will throw off the rest of the problem. So don't forget your diatomics whenever you're doing these types of setups. It's an easy way to throw off your ratio for step 4. But in this case, I gave you the equation, so step 1's done for you. Step 2, convert my known, which is 0.600 grams of lithium, into number of moles. So pause it, take a second, do it. Hopefully you got something that looks like this. If you look on the periodic table, lithium's relative atomic mass is 6.94 grams. So 0.600 grams of lithium would be 0.0865 moles. I would then take that and use that as the limiting reagent, since, again, I only have one known. That would move me to step 4, using a ratio from the balanced equation to convert moles of known into moles of unknown. So take a moment, pause it, set up your system, try to do that conversion. All right, so when you do that, you should get a 1:2 ratio. Again, this is important why you get the balanced equation correct, because as I said, if you hadn't marked it as diatomic, this would have been 1:1, which would have thrown it off by, twofold. So don't forget those diatomics. So when you do this, it's a 1:2 ratio. That means that I get 0.0433 moles of chlorine at the end. Okay. Step 5, convert that into the required units. Required unit is grams. So I do a second molar mass calculation. This time I'm going to do a molar mass calculation involving chlorine. So pause it, take a moment, try to do that. When you do that, hopefully you end up with something like this. Don't forget, chlorine 35.45, got to multiply by 2 to get the molar mass. So when you do that, you find out you get 3.07 grams of chlorine gas is needed to react with 0.600 grams of lithium to form lithium chloride. Right? So one last one here in the mass-to-mass conversion. This will be a more complicated one, going all through the 5 steps. So I haven't given you the balanced equation, haven't given you anything other than just the plain English. So hydrazine is a rocket fuel used in high-end rocket motors. Right? Fuel combusts with oxygen to form nitrogen gas and water. If you have 25 grams of hydrazine in the rocket engine, what mass of water vapor in grams would be produced in excess oxygen? So good news is we're still not worrying about step 3 because we only have one data point, so that's our limiting reagent. We've got all the information necessary to write the balanced equation. So our first step before we do any other calculations in this, so I don't even want you to see, hey, I have this many moles of hydrazine. Don't even do that until you come up with the balanced equation. So take a moment, pause it, write out the balanced equation for hydrazine plus oxygen yielding nitrogen gas plus water. The formula for hydrazine is obviously in parentheses after it. All right, come back. Hopefully you got something that looks like this. Two nitrogens combine to form nitrogen gas. The H's combine with oxygens to make two waters. Fairly straightforward reaction, fairly easy balance, but it's essential. You got to have that balanced equation right in order to get the ratios for step 4 correct. All right, step 2. I have a mass. I need moles. So take a moment. Try to convert step 2. Try to convert your known into moles. All right, hopefully you ended up with something like this. 32.04 grams per mole of hydrazine. 25 grams of hydrazine gives you 0.7801 moles of hydrazine. Right. Step 3 is trivial. Only have one reactant, so it's the limiting reagent. That leads us to step 4. Step 4 is converting moles of known to moles of unknown. So take a moment, pause it, try to do that step for me. All right, hopefully you got that it was a 2-to-1 ratio. Again, these come from the coefficients in the balanced equation. Coefficient on the top is your unknown, coefficient on the bottom is your known. So 2-to-1, that means I get 1.560 moles of water. All right. Step 5, I've got to convert that into the required unit, which is grams. So take a moment, pause it, try to do that calculation. All right, step 5. Grams of water, 1.560 moles times 18.01 grams of water gives me 28.1 grams of water. And that would be my final answer. 3 significant figures. 3 significant figures in the only data point in the problem. This is how I would lay out the solution to this problem if I was writing it out, to try to show my professor I know what I'm doing. Because it's easy to follow, it's easy for me to find mistakes, it's easy for me to judge whether mistakes are trivial and therefore acceptable, or they represent a misunderstanding of the concepts. Okay? So that is a quick breakdown of mass-to-mass conversions in stoichiometry.